Hello, welcome back to EEforEveryone. Today we're going to talk about two very important concepts, power and efficiency. Power is a universal concept that is backed by many principles in physics. Power is the tool through which many electrical systems can be converted into a mechanical analog. Another great thing about power is that 1 watt is equal to 1 volt times 1 amp. 1 watt is also equal to 1 joule per second. This means that if an electrical system is 100% efficient and consumes 1 watt for 1 second, 1 joule worth of work can be done. That's cool, and now that we're talking about joules, something almost magically elegant occurs. This beautiful unit, the joule, is the gateway to some awesome math. Right now, standing on the second floor of a building, I have potential energy. I have done work to gain this energy, and this energy comes from the fact that the gravitational pull of the Earth is always trying to get me to my lowest energy state. The gravitational energy stored in an object is calculated as the mass of an object times the acceleration due to gravity times the height off the ground an object is. This potential energy due to gravity is calculated using the mass, which is usually constant, times the acceleration due to gravity, which is nearly constant at 9.8 meters per second squared, times the height the object is above the Earth. That's what can change. If we want to lift an object that weighs 100 kilograms, 1 meter above its current position, this means that we will need to exert 980 joules of energy. If this object must be lifted in 1 second, that means that we need to use a motor that uses at least 980 watts. If that object needs to be lifted in 0.5 seconds, we will need to use a motor that consumes at least 1,960 watts. If that motor is only 80% efficient when converting electrical energy into mechanical energy, then we would need to use a motor rated for 2,352 watts. Now that's the thing that just drives me nuts. A lot of people don't have proper respect for the watt. I mean, a watt has a physical, real-world meaning about the quantity of useful work something can do. If we buy a tool or a light or anything electrical that is rated as using a certain number of watts, let's say 300. If we go out to the store and buy something rated for 300 watts, actually monitor the voltage and current being consumed by that something when fully loaded, 10 out of 10 times, it falls short. It could be using 100 watts. If we're lucky, I call the watts on a product box or product page marketing watts because they have no bearing on the electrical or mechanical capabilities of a system. This is because bigger is always better, so rating something with its peak output power of peak watts and then calling it watts is a very common practice. Then of course they label it as watts asterisk instead of peak watts because why not? I mean, it's not technically lying if there's a footnote that says 300 watt performance is only guaranteed on the third Friday of every solar year when operated off of a 200 volt generator at 75 hertz at an altitude of 3,000 feet. Gah! It's enough to drive a person insane. If it's watts, call it watts. If it's not watts, then call it something else. Believe it or not, there is more to this story than gawking at how cool physics is and complaining about misusing units for marketing. I made a mistake. Or rather, I'm about to make a mistake. More accurately, both. Making videos makes time confusing. You're about to see something that looks like this. In fact, you'll see exactly this. This is a keyframe from Saturday's video. What I'm trying to do here is calculate the thermal resistance of the entire system from LED junction to ambient air. In a previous video, we estimated that the junction to ambient thermal resistance would be about 6 degrees C per watt. This was assuming a number of thermal vias, thickness of the board, etc. Doesn't that sound great? Well, kind of, except for the fact that we didn't account for any thermal resistance of the heatsink. And then we got a total number of 1.7 degrees C per watt based off of our measured data. What happened? Well, I think we forgot to account for some things. The temperature measurements were correct, so the delta T number is fine, but we've allocated too many watts as being dissipated as heat. We accounted for the 85% efficiency of the AC to DC power supply, which is good. However, we forgot the efficiency of the LED driving circuit, as well as the quantity of power that got converted into photons. You know, the whole point of the project. Let's fix this math by determining the real thermal resistance. Remember, thermal resistance is a constant that relates the amount of power flowing through a system and how hot the hot side of that system is. The units are change in temperature over change in power, or degrees C per watt. Given the output voltage on the LED channels, the driver should be about 94% efficient based on the datasheet. This brings 25 watts down to 23.5. Now the LED converts some of that power into light, but most of that power is turning into heat. I've been looking for a good article on what percent of power is converted into heat, but I can't find anything credible. For now, I'll substitute in something that seems possible, but is erring on the high side, so it'll make the thermal resistance of the board look worse than it would actually be. We'll use 80%. That is, 20% of the power is converted into photons, which radiate from the LED, and the remaining 80% is converted into heat. Sweet. This leaves us with 18.8 watts of heat to dissipate. This is far more than I was expecting. Looks like our math wasn't so far off after all. With a power delta of 18.8 watts and a temperature delta of 43 degrees Celsius, the thermal resistance from the LED case to ambient appears to be 2.3 degrees Celsius per watt. The cooler I am using is rated with a thermal resistance of 0.42 degrees Celsius per watt, making the thermal resistance from PCB to the heatsink 1.88 degrees Celsius per watt, from the LED side to the heatsink. Keeping in mind that each LED has a junction to case thermal resistance of about 10 degrees Celsius per watt, and each LED is dissipating about 1/30th of the total power, the junction of each LED should be about 6 degrees warmer than the case, so around 76 degrees C. With all of these factors considered, the total thermal resistance of the system from LED junction to ambient air is approximately 12.3 degrees Celsius per watt. That's a far cry from the 1.72 we will come up with on Saturday. The thermal performance of the plant light is good. The biggest player by a long shot for thermal resistance is the LED itself, and that heat gets wicked away quickly by the cooling solution. Remember to respect the watt. If too many people start misusing the term, it'll lose its meaning. I don't know about you, but when a tool is rated for 2 kilowatts, that doesn't really mean anything to me. When buying a soldering iron or other more professional equipment, power ratings tend to be a bit more accurate. If you think that respecting power is cool and this video is great, let me know by hitting the like button on this video, subscribing to the channel, or leaving a comment letting us know what you enjoyed. Most of all, I hope you learned something great today, and I hope to see you again soon. Bye!